Okay, thanks, Trace and Randall, for the talk. And now I will talk about how we use reinforcement learning for computer architecture security. So security now presents one of the most challenging problems today. If you think of our system today, we have the cloud and the client, cell phone, mobile devices. From all these devices, the computing stack is almost the same. We have the application on the top. We might have some sensitive application that deal with some medical data, encryption and decryption. And below the application, there is the operating system. And below the underlying layer is always the hardware, which serve as the foundation of the system. If an attacker can go into the hardware, even if they are protecting the OS layer, the attacker can still break in the system. Another concerning point of hardware security is that hardware is difficult to patch once fabricated. Although today there are some way to patch a microcode, but still there are a lot of hardware. The hardware will be fixed after fabrication. If there are vulnerability, and once those device has been deployed, it's hard to mitigate. Yet today, it's quite difficult to build a secure hardware system. As we can see today, we find a lot of vulnerabilities in the system. We might heard of Spectre and Meltdown and all those side channel, covert channel attacks. The main reason that building a secure system is difficult is that it's hard to evaluate the vulnerability because the vulnerability comes from unintentional mistakes or undefined behaviors. So as a system designer, in a lot of cases, the vulnerabilities are not known in the beginning. And today, when we evaluate the security of a system, the methodology is heavily relied on human expertise. So we have a security expert, like people who mostly work on security, to examine the design and see whether there are vulnerabilities. And this evaluation is mainly based on the known attacks and the intuition of the human expert. And based on the vulnerability, people then start to propose mitigations and defense. And again, this defense are designed based on known attacks. So it's kind of a cat and mouse game. And in each iteration of such game, the system becomes more and more secure. However, there could still be vulnerability in a system. Such manual process is quite ad hoc and slow. Take cache timing attack as an example. Cache is first proposed in 1986, and only until 2005, people found, oh, there is vulnerability there. There could be a side channel attack and can leak information. And today, we can still see conference paper talking about novel attacks today. And although there are mitigation proposed, those mitigations are often then be broken by new attacks. So we see it's pretty hard, and sometimes using human to evaluate security is not systematic. They currently have a couple of tools to find vulnerabilities. One is formal method, which it's a rigorous approach to determine if certain security property is satisfied. Another approach is fuzzing, which is automatic testing that we feed in random or unexpected input into a system and see what's the system response. Such methods have their pros and cons. For the formal method, it provides a formal guarantee it's provably secure. However, in the formal method today, we need a formal model of the system. Typically, it means you need a separate code base to formally model the system and then feed that into SMT solver. And such method need white box design. That means you need to know the design details. And also there's scaling limit, like you can only limit to validate relatively small designs today. For fuzzing, the pros is it's very automatic, different from formal method that humans have to formally model that. However, the fuzzing usually require predefined attack sequences or predefined gadget, which limit the coverage of the testing. So when we start this project, we start to think whether we can use machine learning to help this problem, to find vulnerabilities, to replace the human expert. So reinforcement in machine learning, there could be supervised learning or reinforcement learning. As Yuandong present, reinforcement learning today has shown a very exciting result. Supervised learning in the history has been used for security problems. We have seen earlier work how to use supervised learning to help attacker to recover secret in a side channel attack. And also with label data, the supervised learning can be used to train a detector to detect known attacks. It can only limit to known attacks because we need to have a label data set. So when I talked with Chris and Yuandong, we came up with this question. Can we use reinforcement learning to automatically learn system design without knowing the system design, taking the system design as a black box? Can we let the RL agent to learn the vulnerability in the system? Can the RL agent to generate attack sequence that's not specified by human? That means if we do not have any secure expert who have knowledge of prior known attacks, can RL agent without any prior known knowledge of the security vulnerability learn the vulnerability of system? And also can the RL agent can even help design mitigations? So in this line of research, we use cache timing attack in processor cache as a case study. So now we know that previously most security vulnerability analysis are done by the human. We really need smarter tools for secure analysis. Now let's first, I will first give some background on cache timing attacks. The intuition behind the cache timing attack is that cache is shared by applications in a system. So today, if you have a CPU, you run multiple processes in one system. And at OS level, there are logical isolation between different applications. And ideally, the different processes should not be able to see each other's behavior. However, in a realistic system, cache is shared or some piece of hardware is shared between applications. And it's very common to see some victim application have a secret dependent access. For example, if the victim is trying to access an array where the address, the index of the array depends on the secret, or if you have a branch, the branch depends on the secret, and where you access the memory depends on the branch, which branch you take. Such victim secret dependent access will trigger cache replacement and thus change the cache state. For example, here, the victim will access cache and change the cache state. And then the attacker can observe the memory access latency to see whether he get a cache hit or miss, and then infer the victim's behavior. Prior research has shown that such side channel can leak cryptographic keys, like secret keys in AES or RSA algorithms. And it can also break isolation between sandbox applications or VMs. It can also break hardware security features such as the point authentication code in latest ARM processors. Such attack is really concerning because the attacker here only need to observe the latency in software execution. The attacker does not need any physical access, and the attacker do not need privilege level just a normal application level code can learn the behavior of another victim program. And for such attacks, although it's discovered in 2005, it's still developing. It's still not sure whether we know all the attack types, as we see new attacks are still being discovered every year. And another question is, if we propose a mitigation, will there be new attacks against that new mitigation? I want to emphasize that finding attack is challenging. Typically, there are a few steps to find attack. First, we need to reverse engineer the behavior of the design. So if you want to attack a real machine, you first want to reverse engineer what's the cache structure, what's the microarchitecture design of that system. And for processor today, like Intel CPUs, a lot of design details are undocumented. And second step, we need to design attack sequence to expose the information. And third, we need to reduce the noise in the system to get valuable data of the victim process. As I said, for reverse engineering, a lot of processor design details in commercial processor today is undocumented, like the replacement policy, what the prefetcher scheme used in cache today and unknown, are not public. And sometimes defense are implemented in the processor, and this mitigation might not be known. And in terms of attack sequence, with more recent attack, we see the recent attack have actually very long attack sequences. That means this is non-trivial to find those attacks. So in the past 2 years, we are looking at how we can use reinforcement learning to automatically find those attacks and mitigate attacks. And then we have published 2 papers in this year. The first paper I want to introduce is AutoCAD in HPC this year. We use reinforcement learning to automatically explore cache timing attacks. I see from this figure to here, we have a system that's a target, and then typically we need a human expert. But instead of human, here we replace the vulnerability analysis with an RL agent. And the design can be either in simulation or real hardware. The RL agent interact with the environment, can learn the sequence, and then we can see whether there is vulnerability in the system. The key finding of this work is that we find the RL can find a variety of vulnerabilities in this target system, and we can even find a new attack pattern. So the key question here is how we can interact an RL agent with an environment. As Yuan introduced, on the agent side, there are already a number of different types of algorithms that help RL to learn. And the key question here is how we can formulate the cache timing attack as a problem that can be solved by the agent. For vulnerability analysis, we let the agent to play the attacker role. And apparently here, if we look at cache timing attacks, the environment is a cache. The cache could either be architecture simulator or a cache in a real processor, like a cache in my laptop. So then the question is, what's the action space? To formulate this problem, we look at all the known attacks or some representative known attacks. Here, this table lists some very well-known attacks. Most of the actions is for the attacker to make an access, and also the victim to access a memory so that the victim will access an address that depends on secret, which leak the information to the cache. And since here the goal is for the attacker to know the secret, so in the end, we hope the agent can guess the secret so we can evaluate whether an attack is successful or not. In terms of the observation space, we we formulate as the latency of the attacker access. Because by definition, it's a timing side channel attack. The attacker learns the information by measuring the latency of memory accesses. In terms of reward, here the attacker goal is to retrieve victim secret with a small number of memory accesses. So if the attacker, the agent in the end, can retrieve the secret or guess the secret correctly, we give a positive reward. If the attacker, the agent guess the result wrongly, we will give a negative reward or penalty. And we also want to make the attack very efficient to have high bandwidth. So we apply a small negative award for each step. So we want the agent to optimize the number of steps needed for the attack. Here is an overview of our framework. We have the target caching implementation. In this work, we have two versions. One is the caching simulator. We build an interface between the cache and the RL agent. And another is a real hardware implementation that we have a interface so that a RL agent can interface with a processor at runtime. And we also have the attacker and the victim configuration, which define the address space of the attacker and address space of the victim, because there are different threat models in an attack, like whether they are shared memory space or not. These are 4 different threat models. And after training, we extract the trajectory of the RL model. And this will become the attack sequence. With this, we can analyze the attack found by the agent and also can demonstrate such attack on real hardware. And inside the RL engine, we find there's an agent, which we use the PPO algorithm to train the agent, and it's a neural network. And in the environment, first the environment will interface with a cache, either simulator or real hardware. And in the action space, we have the 3 types of action. If it's an attacker access, the attacker process will query the cache through the interface. And the victim process will hold a secret address. If the agent make a guess or the attacker make a guess, the guess evaluator will match that result with the secret address to see whether this is a successful attack or not. So with this, with the PPO algorithm, we train the model. Here is a result we get from simulator. We test many different configuration of cache, including a number of different cache structure like direct map cache, fully associative cache, cache with prefetchers, and cache with multiple levels. Here are the attack sequence found by the agent. And we also manually analyze the sequence, and here the last column is the attack category. We find that the attack find most of them match what we our prior knowledge of known attacks, and also the agent can find non-trivial sequences. And interestingly, we find the AutoCAD actually find a new attack. We find, after analysis, we find it's actually a combination of 2 known attacks from Streamline, which is in SPLOS 2021, and LRU-based attack, that's HPC 2020. And the agent smartly combined the 2 attacks. And so as you see here, the Streamline have overlapping to increase the bandwidth of the attack. And the LRU-based attack uses the replace policy, which is more stealthy than known attacks. And by combining the 2 attack patterns, the resulting attack is actually have higher bandwidth and more stealthy. So we see that because such attack leverage the replace state, it caused no victim cache misses, which lets the attack able to bypass a lot of known mitigations. And we also implement the attack in on a number of different real processors. Here the result. The x-axis is the error rate of the cover channel, the attack. The y-axis is the bit rate, like how fast we can leak the information. We find that the new attack have higher bandwidth than the known and than prior known attacks. We also did a lot of intensive study on the RL agent on different cache configurations and on different mitigation schemes. We find that if there is a no mitigation scheme, very likely the RL agent can find some way to bypass that. As an ablation study, we also studied different type of neural network. We studied the transformer, LSTM, and MLP, multi-level perception. We found that the transformer and LSTM, which is good at processing sequence, are better at deal with such attack sequences. In the second work I want to talk about today is using multi-agent reinforcement learning to help design attack and detection. We see that in AutoCAD, we replace the vulnerability analysis with the RL agent. And in MACTA, we also include the defense as another agent. So we have the attacker agent and detector agent. The attacker agent try to come up with novel attacks, and the detector agent try to detect attacks. And the attack, when we train this together, the attacker will try to bypass the detector, and the detector will try to cover as much attack as possible. So we find that with such multi-agent reinforcement learning approach, we don't need any manual input. And if we train with several iterations, the attacker will be able to act more stealthily to bypass the detector. And the trained detector can generalize to unseen attacks. And the trained detector is more robust and less exposed to new high bandwidth attacks. We found that as we train further, it's harder and harder for the attacker agent to come up with high bandwidth attacks. So in terms of formulation, because here the goal is to train a detector. Detector need to detect an attack scenario, but also want to we also want the detector can handle benign cases. So in such formulation, we have the attack scenario and the benign scenario. And for the attack scenario, we hope that detector can detect the attack. And for the benign scenario, we hope the detector do nothing. For the formulation, the attacker part is exactly the same as AutoCAD, that it observes the latency from cache. The action space is memory access or making a guess. And the reward here, in addition to successful attack or not, we also add reward based on whether the attack is can have a successful attack without an alarm by the detector. For the detector formulation, the observation space is similar to the attacker, that we let the detector to observe all the memory access of the cache simulator. And then for the action space, the detector can choose to raise an alarm or not, depends whether the detector thinks it's a malicious behavior or not. And for the rewards, it will based on whether the alarm is a false alarm or a crack alarm, and whether we have false negative in terms of detection. Here are the results. On the left side, this figure shows how the detection rate for different attackers. And the prime probe is a known attack. The AutoCAD is just an AutoCAD attacker trained without a detector. This is another training algorithm, and this is MACTA attacker versus train against our detector. The green bar here is the MACTA detector, which is our detector with a multi-agent approach here. We find that our detector can generalize to unknown or unseen attackers, while the other approach like CC Hunter or Cyclone, which is the detector in prod, work cannot generalize to new RL-based attackers. And for the MECTA attacker, this attacker is trained against a detector means it is aware of the behavior of the detector, but still our detector perform better than other detectors. The right figure shows the false alarm rate, which means if we only have benign program, how the detector will react. We hope the false alarm rate is as low as possible. And with the multi-agent training method, we find the detection rate, the false alarm rate is pretty low here. So to conclude, we find RL can help both find the vulnerabilities in a system or help design a detector agent. And with multi-agent training method, the detector is very robust. However, there are a lot of things to do in the future. For example, how can we scale this method to larger real-scale cache or to include more attacks in the microarchitecture design? And how we can understand the result of the model, because as attacker agent, the attacker agent will generate many attack sequences. How we can automate the process to analyze the sequences generated by the agent. And can we apply RL for other security problems or even other architecture problems? This work is done by a very awesome team. Thank you for the time. And due to the interest of time, I actually abstract away a lot of details from the work. And later in the lab session, Mulong will tell you how we actually implement the RL agent, the AutoCAD, in the code. And you will get a chance to get your hands dirty and train your agent yourself. And we will provide AWS VM with GPU so you can train the model.